Hello there, welcome to 9-2. We are talking domain of logarithmic functions. And I'm going to start off this lesson. We're going to kind of do an investigative kind of approach. We're going to consider three cases. So if we go ahead and consider the following logarithms, where the argument is positive, 0, and negative. We'll go ahead and we'll change these to exponential form, and then we'll see, okay, is our function defined or is it not defined? So here I have log base 3 of 9, okay, so that's 3 to the power of x is equal to 9, and our function is defined. I can go ahead and come up with an x value, right, that satisfies this, right, so where x is 2. Now, if our argument is 0, all of a sudden I have 3 to the power of x is equal to 0. Well, think about this. Can an exponential function ever be 0? Well, no, it has a horizontal asymptote at 0. Right? There's no value of x I can plug in, right? That will get the outputs to 0. So this is not defined. And then what if the argument is negative? And again, if I have an exponential function without any transformations given, there's no way to get a negative value. Okay, so it's important to note that a logarithm, log base b of a, is equal to end, where our argument must be positive. It must be positive or greater than 0, okay? So, since a logarithm is defined for positive values of the argument a, this means that the logarithmic function must be restricted to values of the independent variable x so that the argument is greater than 0. And that's just what we do in our steps. We'll take our argument, we'll set it greater than 0, set it strictly greater than 0, and then we'll solve the inequality. So we're going to be solving inequalities, and just some things to remember when we're working with linear inequalities and quadratic inequalities. If we multiply or divide by a negative, you'll see your inequality again switch, so don't fall trapped to that. And then when we're solving quadratic inequalities, what we're going to have to do is draw a number line. When we solve, we'll find our critical values, and we'll have to test and see, okay, which interval gives us our domain. So here is our next example. Find the domain of the function. Use set and interval notation. Okay, so step 1, take the argument, and again, argument is the inside, right? What our input is, and we'll set it greater than 0. So 9 minus x is greater than 0, and we're going to go ahead and solve. So I'll subtract 9 on both sides. And we get negative x is greater than negative 9. We'll go ahead, we'll divide by negative 1. So here's Admiral Akbar. It's a trap, right? X is less than 9. We have to switch our signs, right? Okay, so this one was easy. Here is our domain in set notation, x, such that x is less than 9. Okay, and in interval notation, it is going to be negative infinity to 9, both parentheses. If you struggle with interval notation, what I recommend doing is just drawing a number line, and I can place 9 on it, and I want x is less than 9. So that's all the values this way, right? So this will tell you we're going from negative infinity to 9. Another way of thinking about it too is I've been told the inequality points as an arrow, right? So the arrow is going this way, so our domain's that way. Okay, next example. Oh, well, here's a practice. No, here we go. Okay. Example 2. We have the natural logarithm of 4x plus 7 plus 8, and we want the domain. So again, we'll take our argument 4x plus 7, and we'll set it greater than 0. We'll go ahead and solve. For x is greater than negative 7, so x divided by 4. X must be greater than negative 7/4. Okay, so again, as set notation, This is x such that x is greater than negative 7/4. And then for interval notation, that would be negative 7/4 to infinity. And again, they're both parentheses, right? I'm not equaling to that value. That would produce a argument of 0. We don't want that. Yeah. Okay. So there are a couple of examples. I have a practice set for you. Please go ahead and pause the video. Try this example. Okay. So hopefully you've tried this example. Here is the solution. Okay. Did you remember to flip the sign? When you multiply or divide by negative, flip the sign. Okay. All right. Next example, and now what we're going to do is we're going to get into some quadratic examples. Now, quadratic examples are going to produce two critical numbers, and we'll have to go ahead and test. Okay. So step one is the same approach. We have 64 minus x squared. I'm going to set this greater than 0. Now, since this is a quadratic, what we do here is we switch to an equal sign, and I'll write it in a different color just to kind of note this. 64 minus x squared is equal to 0. And now I'm going to go ahead and I'm going to solve this. So I'll subtract 64 on both sides, giving us negative x squared is equal to negative 64. I'll divide by negative 1. We get x squared is equal to 64. And then we'll go ahead and take the square root of both sides, giving us x is equal to plus or minus 8. Okay, so what I've solved for, these are the critical numbers. These are where the argument is equal to 0. So again, we'll draw a number line, negative 8, 8. So here's our critical numbers. And what we want to do is I want to test this. Okay, and remember the best number to test, always, 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 0 and 1. There's, I guess, 2. But 0 is the best. So what we do is we plug it into our original inequality. I'm going to plug it in right here. So 64, take away 0 squared, which is 0. So 64 is greater than 0. Is this true or false? That is true, right? So that means that our domain is going to be positive in this region. So all values in here, this is our solution. On the outside, right, if I plugged in any values out here, I would get a non-true statement. Those are negative argument values, right, which our function's not defined there. So we have to go ahead and define this as our domain. So in set notation, our domain is the x values such that x lives between negative 8 and 8. So negative 8 is less than x, which is less than positive 8. Okay, and an interval notation, that would be negative 8 to 8. Again, parentheses, right? We're not including the 8s. Okay, they produce an argument where it is 0. Okay? All right. One more example. Here we have the natural log of x squared minus 20. Okay, so x squared minus 20 greater than 0. And then I'm going to go ahead and switch to an equal sign. And then we'll solve. Okay, so add 20. We get x squared is equal to 20. So x is equal to plus minus root 20, which is 2 root 5. Okay, so again, these are our critical numbers. So we'll go ahead and test them. So negative 2 root 5, positive 2 root 5, and we'll test 0. So when I plug in 0 into my logarithmic argument, we get 0 minus 20 is greater than 0. And this is false, right? Negative 20 is not bigger than 0. So we know that this is not the solution region, right? I'm going to have negative argument values here, and on the outside, I will have positive argument values. Okay, so that's our restricted domain. Okay, so sorry, I'm looking at my notes. Set. Right, and think about it like this. Okay, so x values such that x is less than negative 2 root 5, or x is greater than positive 2 root 5. Okay, so that's our set notation. And in interval notation, that would be negative infinity to negative 2 root 5. Union, right? Now we gotta cover this area. Okay, positive 2 root 5 to positive infinity. Okay. All right. I have a practice problem for you. Please go ahead, pause the video, and try this example. All right, hopefully you pause the video. Here is the solution. Okay. And I'm going to go ahead and stop the video here. I'm going to make a secondary video that has a couple more examples and practice problems. All right, catch you next time.